This is called lesson 3. I'll title it as lesson 3 or the day 4 lesson. This lesson is titled as the continuity and the intermediate value theorem. Part 1, in first part of this lesson, we will talk about the various types of continuity and discontinuity, I should say, and also the definition of what it means for a function to be continuous at a point C and what it means for a function to be continuous over its entire domain. So let's start with that definition right there. Okay, you have seen this last year in your AB course. A function is continuous, it's at point C if the limit of that function as the x approaches C matches what the defined value of that function is at x equals C. Okay, so once again, a function is continuous at an interior point C if the limit of f of x as x approaches C matches the value for f of C. The limit matches the defined value. So for instance, okay, take a look at the first picture that okay, to illustrate this point. I'm just going to pick an arbitrary x value and call it a C. And let's take a look at how that is defined and also how the function behaves near C. For this graph, as you could see, at point C and also near point C, you clearly have a limit value. And what is a limit value right there? Limit value appears to be the y value of the function itself, okay, which we could write it as f of C. And as you could see, this is an instance where the limit of the f of x as x approaches C from either side does match what the defined value is, f of C, right? You can see that, right? So whenever the limit value matches the defined value, then the function is defined to be continuous at that point, at that x value, at that particular x value. Something that is not continuous could be illustrated by the second graph that you see on the first page of our notes. It may be difficult to see, but there is an open circle at x equals 0. Okay, so we will consider, okay, we'll use x equals 0 instead of saying x equals. Okay, so we're gonna be concerned with the x value of 0. And as you can see, though the limit exists, okay, so limits of the f of x as x approaches 0 is equal to 1. But here's the problem, okay, this is problematic. However, f of 0 does not exist, right? It's not defined or undefined. Okay, so we clearly have a case where the limit of f of x as x approaches 0 does not match the value for f of 0 because again, this is undefined while this part is equal to 1. 1 is clearly not equal to undefined. Okay, let's take a look at other cases. Okay, by the way, this second graph is an example of what we call a removable discontinuity. And a removable discontinuity is simply a hole. Okay, it's discontinuous because you have a hole. You have one small hole at that one singular x value where your limit value will not match, as you could see, the defined value, or the defined value isn't there at all. Okay, so similarly, let's take a look at the third graph right here. Okay, so once again we have a removable discontinuity at x equals 0. The only thing different about this question is that even though you have a hole on the graph itself, okay, the function itself, okay, but you have another point that is above the line. Okay, the function behaves like a line except when x equals 0. So how do we show that the function is not continuous at x equals 0? Well, we take a look at the limit value for it first. The limit of the function f of x as x approaches to 0 from either side. Clearly, you could see that that value would be 1. From the left side, the y value is becoming 1 as the x value approaches to 0 from the right side, it's the same case, right? So you can see that the limit would be 1, while the defined value at x equals 0 is not 1. Okay, in this case, f of 0 would be 2. So clearly you could see that the limit of f of x as x approaches 0 does not match f of 0. Okay, so that would be your justification for function not being continuous, this particular function not being continuous at x equals 0. So not continuous at x equals 0. Okay, take a look at the third graph. For the third graph, it looks like a part of what we call a step function, or it could just be a piecewise function where you have the left side and the right side. Okay. Once again, intuitively, we know that this is not continuous. Okay, but more formally speaking, okay, your limit for this one as x approaches 0 from either side does not exist at all. So we cannot even compare, okay, while the f of 0, the defined value at x equals 0 is equal to 1. But again, okay, these two are not congruent. So you could say that the function is not continuous. The function itself is not continuous at x equals 0. Okay, for this reason. Okay, this is an example of what we call a jump discontinuity. Okay. This one is an example. The fifth one is an example of what we call an infinite discontinuity. Now, how do we justify formally that this is not continuous at x equals 0? There's two ways to do this. Okay, you could clearly see that there's no limit for this one at x equals 0. That's one way. Okay, that you could again come to conclusion that this is not continuous. Another, okay, it fails the second condition as well. There is no defined value at x equals 0 anyway. There is no f of 0. Okay, so the limit does not exist at x equals 0 or as x approaches 0. And f of 0 is also undefined. You don't have a single defined value for f when x equals 0. Okay, and similarly, okay, we have a rare case. Okay, the last one is an example of an oscillating discontinuity. Okay, but you will not see this too often. Okay, but this is a favorite example of many textbooks. They like to illustrate this with using sine of 1 over x. Okay, so this is your summary of, again, something that is continuous at point C and something that is not continuous at point C or at a particular x value right there. All right, so let's take a look at some examples. Okay, some practice problems here on your own. This is not necessarily an assignment, okay, but optional practice and examples for us to try to again revisit this topic, this concept of continuity. For 23 and 24, find each point of discontinuity. Pretty easy to find, right? Okay, part B, which of the discontinuities are removable and which ones are not removable? Okay, so I see a typo there. And part C, justify why f of x is discontinuous at that particular point. Okay, so if you look at number 23, you do have, okay, let's actually point out where the removable discontinuities are. So it appears to be x equals 0. X equals 1 will be a jump discontinuity, not a removable discontinuity. Once again, removable discontinuity is just a single hole where you could, if you're able to somehow fill in that hole, the whole function will be continuous. Okay, but x equals 1, it wasn't just a single hole, that you have this gap from the y value of 1 to y value of 0, right? So that's what we consider to be, that's the distinction right there between a jump discontinuity versus a removable one. So for 23, I think that's all I see. Okay, I only see a single removable discontinuity at x equals 0. Okay, So not removable, but nonetheless discontinuity. A discontinuity would be at x equals 1. And part C, justify why f of x is discontinuous at this particular point. At x equals 0, it's pretty easy, right? The limit does not match the defined value, right? The limit of f of x as x approaches 0 does not match the defined value at 0, x equals 0, because this would have been the y value, okay, or the limit value, I should say, for f of x at as you get closer to 0 from either side would be 0 as well. But the defined value for f at x equals 0 would have been 1. Okay, so obviously 0 does not match 1, so that is your justification right there. For the second part, x equals 1, why is this function discontinuous at x equals 1? Because the limit, we can't even compare these two values because the limit does not exist. And you could even stop there. And that right there will be your justification for the discontinuity. You could try 24. Now, let's take a look at 19, 47, and 48. These kind of questions are very common questions that you may see with this topic on the multiple choice section of the AP exam or the practice AP exam or what have you. Number 19, let's take a look at this one. Okay, part A, find each point of discontinuity. And part B, which of the discontinuities are removable, not removable, and lastly, give reasons for your answers. Okay, so point number 19, we're not given the graph, we're just given the rules for this piecewise defined function. If I want to sketch it out or if you want to Desmos it, that's fine. Okay, but I'm going to assume that this is a non-calculator question. 3 minus x would just be a line that has a slope of -1, starting with the x value of 2 on the left side of the x value, left side of 2. Let me see. So when x equals 2, so 3 minus 2 would be 1. It's an open circle and then has a slope of -1. Gosh, not the best graph. So 3 minus 1 would be, let's see, what do I have here? 3 minus 2 would be 1. Open circle right there. 3 minus 2. 3 minus 1 would be 2. And then 3 minus 3 would be 0. So on the left-hand side, you have this graph. On the right-hand side, let's see, 2 over 2 is 1. 1 plus 1 is 2. But that's an open circle as well, 2, 2. And it looks like it's a line that has a slope of 1 over 2. So up 1 and over 2. Okay, so there you have it. Okay, so it looks like you have a piecewise defined function that is not connected. Okay, nor is it defined on the corner points, the endpoints of the either parts right there, as you can see, right? So your justification for this one is that could be that limit does not exist. So that could be sufficient, or you could start with the right side of the definition of continuity, or the fact that f of 2 is undefined. Either one's fine for your justification, or you could use the full definition. The limit of f of x as x approaches 2 does not match f of 2. Again, because this is undefined. Undefined is a little different than does not exist. Okay. It's not like a single value where you could match. Okay. So that's number 19. Number 47, let's take a look at this one. Okay, find the value of a so that the function becomes continuous. Okay, looks like the problem got cut off. Okay, find the value of a. Find the value for a so that the function is continuous. So let's take a look at the endpoints of where they're supposed to meet. So when x equals 3, you got 3 squared minus 1, which is 9 minus 1, which is 8. Okay, so we know that f of 3 is equal to 8. And when x equals 3 for the second one, the second row right there, so 2 multiplied by a times 3 would give me 6a on the right side. Okay. Now, as long as these two numbers are matching, then the left side of the piecewise function will connect to the right side of the piecewise function, and we have a closed circle anyway on the right hand side. So then this function will be continuous at that point. So now we just gotta match, okay, 8 with the 6a. We just gotta solve for a. Your a value would be 8 over 6, which is equal to 4 over 3 right there. So as long as the a value is 4 over 3, we'll then be able to connect these 2 points and then say that the function f of x is continuous at x equals 3, in fact continuous everywhere, because again x squared minus 1 is continuous everywhere on its domain, and because 2ax, okay, or 2 times, I guess in this case that would be 8 over 3x, would be continuous. It's a line that's continuous over its domain, so the whole thing will be continuous. Okay, so you could use the same reasoning for number 48 as well. Okay, there you have it for continuity.
Class, here's the second half or the last part of today's lesson. It's known as the Intermediate Value Theorem, or simply known as the IVT. IVT is, again, one application of the concept of continuity. Functions that are continuous on intervals have properties that make them particularly useful in mathematics and its applications. One of these is called the intermediate value property. And a function is said to have the intermediate value property if it never takes on two values without taking on all the values in between. So take a look at theorem 8 right there in that box. Okay, we again have an intuitive understanding of this, I'm sure. You have a continuous function on a closed interval a to b. Then that continuous function will take on every value in between f of a to f of b, namely what we know as f of c, or you could label that as y naught right there, as you can see. So once again, a continuous function on a closed interval from a to b will take on every y value, guaranteed to take on every y value in between f of a, which is the corresponding y value for a, and f of b, which is a corresponding y value for b. So there has to be a y value in between f of a and f of b. That is assigned to the x value c right there, as you could see. So we'll look at some examples with this one as well. Alright class, okay, let's take a look at an example, or perhaps two, for the application of the intermediate value theorem. We have seen this one in class. Okay, so we could go back to it if you need to, but okay, right now I want to show you at least one of these two right here. I think most of you will be curious about part B, how to apply the intermediate value theorem with part B. For this one, it's not equal to a single value. You don't have a function that equals to a single value, but rather it equals x. But we can manipulate that. Okay, we could tweak this equation to make it into a new function that consists of the difference of the cosine, a trig function, and a linear function. So cosine of x minus x, note that it's not the x minus x, but it's cosine of x, the function itself right there. Whatever that value is, subtract 2x. That has to equal 0. Okay, we want to show that there's a solution to this. We don't have to find that solution, but we want to show that there has to be at least one solution to that in this interval 0 to 1, over 0 to 1. Can we apply the intermediate value theorem first of all? We could apply the intermediate value theorem because the cosine of x is a continuous function on its own over all real numbers. Likewise, x is a continuous function over all real numbers as well. And the difference doesn't really make a difference to that as well, no pun intended. Okay, it's still going to be a continuous function over all real numbers. So certainly it's continuous over the closed interval 0 to 1. Okay, so continuous over 0 to 1. So that's our precondition for applying the intermediate value theorem. So now let's think about, okay, so this is your a. This is your starting x value, this is your ending x value. So now, since f is continuous over the closed interval 0 to 1, And since f of 0 is equal to, that's cosine of 0 minus 0, which would just be 1 minus 0, which will be 1. And f of 1 appears to be, it was, as far as I recall, it was like negative 0.45, but let me double check it here. So make sure your mode is in radian mode to evaluate this trig equation. So cosine of 1, subtract 1 to it, and then you get about negative 0.4596, about negative 0.46. Since this is true, then we could say that by the intermediate value theorem, all of the y values in between 1 and negative 0.46 are guaranteed to exist in this function f. So there has to be a x value, we'll call it x equals c, such that f of c is equal to 0. Okay, why 0? Because again, it's we wanted to find the root, or the x-intercept in this case, pretending that this is a function, and because 0 is in between negative 0.46 and positive 1 right there. So that's, once again, that's an example that involves you to justify something using the intermediate value theorem.